Hello everyone, welcome to this online course on material science. This is lecture 24 in the module 1 on magnetism. If you recall, in the last lecture I have derived the expression for the magnetization of a paramagnetic ion using a quantum mechanical approach and found that the magnetization follows the saturation magnetization times the Brillouin function, right? Which was labeled by J and a function of some parameter Y, and the saturation magnetization was defined as the number of electrons times the Landé factors times the Bohr magneton times the quantum number J, and the function, the Brillouin function Bj labeled by J and Y was given by 2 j plus 1, twice j divided by 2j cot hyperbolic 2 j plus 1 by 2 j, then y, and the second expression is 1 by 2 j cot hyperbolic y by 2 j. And if you recall that this Brillouin function in form differs from what we get from the classical treatment of paramagnetism, which was the Landé function, right? And let's try to understand how quantum mechanics and the classical description differs, right? So for that, just remember that for classical treatment, instead of this function, you had the Landé function, right? So let me plot the Brillouin function. This function B is known as the Brillouin function, right? And if you plot this function as a parameter function of y, right, you can see there's a bunch of curves for different values of j. So if you vary the j, then you will have different curves. So here is j is equal to, so in this notation, this is capital G is our small j, they're the same thing. So j is running from, let's say, plus half and then 1 and all the way up to some infinity, right? So you can see the curve is changing its shape as the value of j is changing. The first point to note is that which of this curve is the classical one, the Landé function. And the interesting point is that, and this is the function for which the index j has a value infinity, is the classical Landé function. Let's try to understand that how that's the case, right? How can we show that when the quantum number j becomes infinity, what that means actually is that the quantization is gone, right? Because if j is infinity, then the quantum number is like minus infinity to the plus infinity, right? So then this is just a continuous number. So if there are infinitely many possibilities of mj, and there is no quantization, right? So classically, when I say j is infinity, that's like the classical limit. And my attempt here is to show that when j is infinity, Brillouin function reduces to the Landé function. And that's the function that we are after for this time being. So let's say how we can convert the Brillouin function into the Landé one with this limit. So we are saying that j should be infinity. So in that case, what is the function itself? The function is 2 j plus 1 divided by 2 j cot hyperbolic 2 j plus 1 by 2 j x, right? Or sorry, the y, the parameter y, and then minus 1 by 2 j cot hyperbolic y by So that's a y by twice j, right? That's our function. And you can see we can just, for the first term, we can change the way we write the terms. So here I want to write it as 2. So we're dividing by j, top and bottom. So we get 2 plus 1 by j divided by 2. And then here we have cot hyperbolic 2 plus 1 by j 2y. And for the second part, I want to approximate the cot hyperbolic function. So we have 1 by twice j and then the cot hyperbolic y by twice j. So let's try to understand what is the cot hyperbolic of any function. Let's say y. This is nothing but 1 by y plus y by 3, and then we have y cubed by 45. So you can understand the series goes on, but if y is small, then we can neglect like these cubic terms and the terms afterwards. So that's why cot y will be approximated by 1 by y and y by 3. So here the argument is y by twice j. So if I want to make this approximation, it will be twice j by y and then y by twice j3, right? Sorry, y by twice j times 3, because we have a factor of 3 here coming from this 3, right? So let me just ensure that we have some 2j3, and you can see now if I put the limit here, this is 0, so 2 and 2 becomes 1, so this is 0, 1 by infinity is 0, 2 get cancelled, so it's cot hyperbolic y. Here the second term has 2j squared term and on the denominator, so when we put j is equal to infinity, this term vanishes, but this is and this j and this j is cancelled, so and half is half by cancelled by this 2, so we have a minus 1 by y here, right? So once I put the limit, you can see that this is nothing but cot hyperbolic y minus 1 by y. And if you recall from the classical treatment of paramagnetism in the previous lecture, this is indeed the Langevin function, right? So that's how you recover your classical treatment from the quantum mechanical Brillouin function by putting j is equal to infinity. That's really one good point to remember. And also you remember that the paramagnetic material has tendency to disrupt its thermal or should I say the magnetic moments in the paramagnetic material gets randomized with the thermal fluctuation, and the material usually follow the famous Curie's law, right, where it says that susceptibility is some constant times the temperature, inversely proportional to the temperature of the system, right? That's the famous Curie's law. So my question is that can we derive this or go to this Curie's law from our Brillouin function, right? That's another interesting possibility of this more advanced function. So the Brillouin function is the fully quantum mechanical treatment of paramagnetic atom, but from that we are trying to see that whether we can go back to the classical model, the Langevin function, whether we can like find out our or recover our Curie's law, which is like a classical treatment of magnetic moments, right? So to derive the Curie law, we have to understand one limit here, is that what is this y, right? If you recall in the last lecture, we kind of let y to be some quantum number j times some quantity x, and if you recall, x was nothing but mu b times the magnetic field divided by kbt. And if I remember correctly, I think we have also have a lambda g factor, right? That was our x, and y was of this sort. So if you put the value of x here, we have j, g, mu b, b, kb, like all these things. In standard experiments, can we guess the values of this quantity and find out what usually the value of y is, right? Let's say we know what is the Bohr magneton. Let's say the magnetic field is 1 Tesla, which is standard, right? In the laboratory, you can apply 1 Tesla magnetic field. And let's say our kbit is known, right? The Boltzmann constant. And temperature, let's say, is room temperature, 300 Kelvin. So you know what is T. And let's say the lambda g factor is 2. And also the quantum number j is half, right? These are standard values of some experiment. So we are trying to estimate the value of y, right? So if I put all these quantities in this expression, you will see that y is not really a very big number. Usually, once we perform this calculation, y becomes 2 into 10 to the power minus 3. That's a very small number and much less than 1, right? So in this limit, we will see that our Brillouin function really recovers the Curie's expression, and let's try to understand how that happens. So our Brillouin function in this original form, we have 2ij plus 1 divided by 2ij, and then got hyperbolic of 2ij plus 1 2ij, right? That's the first term. And on the second term we have 1 by 2ij and got hyperbolic of y by 2ij, and we will approximate our cot function using this approximation, right? 1 by y and y by 3. Because y is a very small number, we can neglect the higher order terms. So let's do that approximation here. So we have 1 by 2ij plus 1 divided by 2ij. The cot hyperbolic, that's our argument. So 1 by y, right, of that quantity, which is let me check first. It should be 1 by y and then y by 3, right? Yes. Okay. So here what we will have is that one inverse of this quantity, which is 1 by the argument, right? So let me write down the approximation here, that this factor stays the same, and cot is approximate by 1 by y minus, plus y by 3, right? So y is, I mean the argument by 3, not y by 3. So that's our approximation for this cot hyperbolic function. That's the inverse of argument, and that's argument by 3. And for the second term, we will have 2ij outside and then inverse of the argument first plus argument by 1/3, right? That's our expression. Now you can see, if I multiply out these factors, what we have for the first term is 1 by y, then 1/3 of 2ij plus 1 whole square divided by 2ij square, right, from this term. And then from these two terms we will have 1 by y minus 1/3 y by 2j whole square. This 1 by y get cancelled, and from here you can see that. So I am just trying to write the terms the way this is written here. So we have, I think we missed a y here, right? Yes, because it's a y by 3, so that should be a y here. Okay, so we have this term and then minus this term. From that you can see we can write 1 by 3 and then 2ij whole square. Here we have 2ij plus 1 whole square, and here we have, right, 1 times factor y, right? You can simplify this 2ij 1 plus whole square minus 1, and you can see this term will give you 1/3 j plus 1 divided by j square y. So this j and this j, you can, so we have 1j left here. So this term will give you 1/3 j plus 1 divided by j and y. What is y? Y is jx, right? So let's put the x back. This j get cancelled. We have 1/3 j plus 1 x, right? So we don't have this. This is only 1/3 j plus 1 x. And now we can estimate the value of the magnetization, because we have kind of approximated this Boolean function in terms of this, and this term sometimes you will see is written by this extra j factor divided by the same j, right? So it's the same with this quantity. And now let me put this value in the expression for the magnetization. So magnetization is nothing but the saturation magnetization times this Boolean function. So, and ms is nothing but n g mu b times j, right? And the Boolean function we just derive is j, the approximated by j plus 1 j times x. And in this form you can see that we can kind of get rid of this j. We have 1/3 n g mu b jj plus 1. So let's put these values here. We have n g mu b by 1/3, right? And let's see what we have left. We have j plus 1, and instead of x, what we can write, you remember what is the value of the x in our expression, right? So if I remember correctly, x was g mu b by kbt. So we have g and g, so that's g square. We have mu b square. So let's organize these terms. If we have the number, we have g square, we have mu square, then j plus 1 times j, then we have the magnetic field m divided by our thrice kbt, right? And you can see that m by b is nothing but this factor, right? N g square mu b square j plus 1 divided by thrice kbt. And why we do care about this m by b? Because our plan is to find the magnetic susceptibility, right? Which is nothing but the permeability times m by b. So if you now just put the value of mb from here, you will have n g square, then mu b square, right? j plus 1 divided by thrice kbt. Okay, and now you can see one thing from this expression is that if I assume all these things by some number, right? Because j is the quantum number, so if you put some values of j, you will get a number out of here, and every other thing is some number, right? So this is, and we have a t in the denominator, so this is like some constant by t. And that's the famous Curry's law, right? So in the limit where y is very small, the Brillouin function is just giving you the Curry's law of paramagnetism. That's the beauty of the quantum mechanical model, right? That it explains the general case, and then if you push the model to a different simplifying limit, it will recover different classical results. And that's kind of telling you that there is something really much deeper about this quantum mechanical model, because we can kind of trace back to every other models that we have discussed using the classical approach, right? I think this should be the end of our discussion about paramagnetic material using quantum mechanical treatment, and thanks for listening.